All right, here we go. Section 3.6. This is the last section in chapter 3, and we're going to talk about proportional and non-proportional relationships. So notice on your notes, I've got all kinds of talk about proportional relationships and then a couple examples, and then I've got all kinds of talk about non-proportional relationships and examples. Proportional is going to be really easy. It's going to feel like we've already done it because it is very, very similar to our direct variation. The equation is of the form y equals k times x. Remember, k is the value that stands for the constant of variation, or the unit rate, or the slope. So those are all very similar. This is the big star moment right here. It passes through the origin when it's graphed. If it doesn't go through the origin, it's not proportional. And I mentioned this already, but direct variations are an example of proportional relationships. We use this a lot in real world data. Actually, the practice problem is going to sound very familiar, but we use this a lot for proportional. We're going to do an activity with these, and we can represent this with a table, a graph, an equation, a statement. An example of a proportional relationship in real world would be money, right? Like a job. How much you earn depends on, or how much you work, and that K value would be how much you make per hour. Now, remind me when we get to non-proportional, because I'm going to ask you about, a work like, say, babysitting, how much you make, as opposed to a job like, say, where you're a waitress, where you make an hourly wage and tips. So we'll talk about the difference between proportional and non-proportional. Hopefully I already know what the answer is going to be as to which one's which. So let's go skip right to example 2. This table shows the number of miles driven for each hour of driving. So in 1 hour we drive 50 miles, in 2 hours we drive 100, in 3 hours we drive 150 miles, and in 4 hours we drive 200 miles. Graph the data. That's easy, right? Let's count by maybe tens? No, 20s. Count by 20s on the y. Count by 20s because we got to get up to 200. So 1 goes to 20, 40, 50. 2 goes to 20, 40, 60, 80, 100. 3 is 150. And 4 hours is 200. So there's our graph. I'm not going to connect those dots, but this is the number of hours down here on the x-axis. This is the miles driven up here on the y-axis. We've got ourselves a graph. What's the relationship between the hours and the miles? Let's say it this way. For every 1 hour, how far do you drive? 50 miles, right? There's our relationship. For every 1 hour you drive 50 miles. Notice the relationship includes those labels on the x and y axis or in the x and y values on that table. Write an equation to describe this relationship. Well, didn't we just say the rate of change? Rate of change equals how many miles do we go for every hour? Our rate of change is 50. Well, that's also our K value, right? Rate of change, constant of variation, slope. We could look at that equation and see that the slope is 50. We rise 50 and we run 1. So we could say that our equation, if we start off with y equals k times x, we put that 50 in for the k, so our equation is y equals 50x. And then use your equation to predict the number of miles driven after 8 hours. Well, the x is what stands for hours, right? 50 miles for every hour driven. So we'd say y equals 50 times 8, which means we're going to drive 400 miles. Sorry. In 8 hours. Look good to everybody? That seems pretty easy, right? Does this equation go through the origin? If we drive 0 hours, how many miles will we go? So it does go through the origin, so this is a proportional relationship. It's got goes through the origin and it has a rate or a k or a constant of variation. All right, so let's talk about these non-proportional. Non-proportional relationships means that we've still got a linear graph. However, it does not go through the origin. So to write an equation, there's two things you can do. You can do these two things, which you're going to, if you know about writing equations of lines, you'll do those two. If you don't, you'll do this guy down here. I'm going to show the second option because that's where I think most people are going to be at. But if you are good with identifying the slope, M, and the y-intercept, B, feel free to do that. If you're not so sure about that, our other option is to test a point XY ordered pair and adjust. So I'm going to do it that second way just so that you can see what we're doing. We're going to always start with, I should add this to the start with y equals kx. All right, so let's do an example or two of these guys, non-proportional. So let's do this. Write an equation in function notation for the graph. Let's worry about that function notation and for just a second. Everybody remembers, right, back from when we did this before, y equals kx is the same as y equals mx. We're going to write an equation and we're going to do some adjusting. So that was that second option. So first of all, let's look and see what our slope or our k is, our rise over run. Be careful on this. This point right here, it looks like it's counting by 2's on the y-axis, and every grid mark is 2, so this looks like it's a 1. So I go up 1, 2, 3, and over 1. Up 3 and over 1, up 3 and over 1. So my rise over run is up 3 over 1. So does everybody agree that my rate of change is 3, or my constant of variation? So I'm going to do y equals 3x. I'm going to highlight this 3 right here and make a little note. That is my slope or my rise over run. I'm also going to highlight out here, I have to adjust. Because if you look at my graph, does my graph go through the origin? It doesn't, right? This is non-proportional. No, it doesn't go through 0, 0, the origin. So my equation is not just y equals 3x. My equation is going to be y equals 3x plus or minus something. So let's find ourselves an ordered pair on here. Looks to me like 1, 1 is an ordered pair. Does everybody agree that 1, 1 is a point on that graph? I could pick any point on that graph and it would still work. Well, 1 is my x value. 1 is also my y value. So I'm going to put those numbers in. I'm going to put a 1 in for the y equals 3 times. I'm going to put a 1 in for an x. And I'm going to put a little box or something right there because I'm going to adjust. Put a plus in there. So 1 equals 3 times 1 plus something. 1 equals, we know 3 times 1 is 3, right? 1 does not equal 3. What do you have to do to make it so that 1 equals whatever's on that other side? What do we have to put in that highlighted spot to make a true statement? What do you have to add or subtract? A negative 2, right? Now we know that 1 equals 1. So my adjust value is negative 2. So I could say y equals 3x plus negative 2, or y equals 3x minus 2. Either one of those two would be right. It's kind of a cool way to do that. And we should mention the function notation. Remember, this is just the fancy. We can change that y to an f of x equals 3x plus negative 2, or f of x equals 3x minus 2. So let's do one more of those. Let's do one with a table. Write an equation function notation for the table. So we're going to start with y equals mx, and we're going to adjust. We're going to do something in there. It looks to me like 0, 0 would not be an ordered pair because my y values are getting smaller. So what is, in order to get started, we need to find our rate of change or our slope. So it's going to be our change in y over change in x's. Remember our rise over run. So how are our y's changing? Whoops, change in x. Our y's, what's our pattern? We keep looking for patterns. We're going to subtract 1. What is our change in x's? Pattern for x's is add 1. Negative 1 over 1 is the same as negative 1. So there's my rate, my m, my constant of variation, whatever we're calling it, they're all the same thing. So when I go to my equation, I'm going to do y equals, I'm going to put that negative 1, x, and then I'm going to have some kind of adjusting over here. So let's pick an ordered pair, any ordered pair. It doesn't matter which one you pick. Let's pick 3, 1. They will all give you the same thing. So we're going to try out 3, 1. 3 is my x, 1 is my y value. So that means I'm going to put a 1 in there for the y. I'm going to put a 3 in there for the x. And then I'm going to put a box or highlight right here so that I remember I've got to adjust. It's probably not going to be a true statement. So 1 equals negative 3. I totally disagree. What do you have to do to that negative 3 in order to make this a true statement, that it is equal to 1? 1 equals negative 3 plus 4. Would you agree with that? Right now it's 1 equals 1. So that means my equation is going to be y equals negative 1x plus 4. Y equals negative 1x plus 4, because the negative 1 is the slope. The 4 plus 4 is how much we had to adjust. And of course, I could write that in function notation. I would just switch that over to an f of x equals negative x plus 4. Remember, you never have to write the 1. So both of those would be good. These ones are a little bit more practice. So I'm going to ask you a couple questions about proportional and non-proportional. How can you tell the difference on a graph between proportional or not proportional? On a graph, I didn't even ask you about a table. And here's a good practice problem for you. If an electrician charges $45 per hour plus $50 for a house call, how much will it cost for 6 hours of work? I want an actual dollar amount. But then I'm asking, is this proportional or not proportional? So the first question, tell me how much it's going to cost for that electrician. Second question, is it proportional or not? A similar question would be that one I mentioned about the waitress or a waiter, doesn't matter. If they make a certain amount of money plus they make tips, is that proportional or not proportional? I'm going to ask you that in class when we talk about this. That is it for section 3-6. Bring your questions with you. Have a great day, and we'll talk to you later.